These will be the practice problems that help you make sure you're ready for our mid-Unit 4 test, which will be on Friday. These questions were hand-selected to be as close to the material that will be on the test as possible. So in our first problem, it says W gives the weight of a puppy in pounds as a function of its age T in months, and they want us to describe the meaning of each statement in function notation. So make sure you understand that gives is an important word here. Anytime it tells you what the function gives, the very next thing is your output. So weight of a puppy in pounds is your output. Then we have the words as a function of. Anytime you see these words, the very next thing it talks about is your input. So age T in months. This is your input. If you remember, in function notation, we always have name, input equals output. So, here we see W of 2, so 2 is our input. And our input, we said, was age in months. It equals 5, and we said what it equaled is our output, so 5 is the weight of a puppy in pounds. So this function notation says a 2-month-old puppy weighs 5 pounds. Number 2, we don't have what the functions equal, so what we have is 6 in parentheses, which is 6-month-old puppy, and 4 in parentheses, which is a 4-month-old puppy. But we know that the function gives us the weight. We just don't know what that weight is. So number 2 says that the weight of a 6-month-old puppy is greater than a 4-month-old puppy. And finally, number 3, again, it's not telling us how many pounds the puppies weigh, but we do know that the function talks about the weight of the puppy in pounds. We know that the number inside parentheses is our input, which we said was the age in months of the puppy. So number 3 says the weight of a 12-month-old puppy equals the weight of a 15-month-old puppy. So this question makes sure that you understand how to read the description of a function notation and then interpret what the function notation represents in the context of that description. So our next question, function f gives, again, we have the keyword gives. The next thing will always be the output. So function f gives the distance of a dog from a post in feet. This is the output. Then we see the key terms as a function of time. Anytime we see that, the very next thing we talk about in seconds, since its owner left, that is the input. So they want us to find the value of f of 20. So remember, in parentheses is your input. So if we want the value of the function f at 20, we go over to where 20 seconds, we go up until we hit the graph, and then we look left to see what the value is. And at 20 seconds, the value is 3 feet. So f of 20 equals 3. Now we want the value of function f at an input of 140. So that represents 140 seconds. We go up until we hit the graph, and then we look left to see what that y value is. And we can see that y value is approximately 3.5. So f of 140 seconds equals approximately 3.5 feet. And this is how we would find the value of a function at a given input. This graph represents Andre's distance from his bicycle as he walks in a park. Decide whether the following statements are true or false. So if you notice, time in seconds is our input. So as the graph goes to the right, the time in seconds increases. Distance in feet from his bicycle is the output. So as the graph increases up, the distance from his bike is increasing. Number 1, the graph has multiple horizontal intercepts. So if we look, horizontal intercepts are where they touch the x-axis. So we have one intercept right down here at the beginning around 0 to 1 seconds. Then if we continue along the horizontal axis, we have another horizontal intercept down here around 25 seconds. So we can say 1 is at 0, 0, and the other horizontal intercept is at 27, 0. So this one would be true because we have a horizontal intercept when Andre first starts to leave his bike, and we have a second horizontal intercept when Andre returns to his bike. Number 2, a horizontal intercept of the graph represents the time when Andre was with his bike. So a horizontal intercept represents a distance of 0 feet from his bike. So this would represent when Andre was with his bike. That is true. Number 3, a minimum of the graph is 17, 1. So a minimum is the lowest point on the graph. And at 17, 1, we would be right in this area here. Now that could be seen as a relative minimum because it's lower than the points around it, but it is not the minimum because the minimum would be the horizontal intercepts at 0, 0 and 27, 0 because a y value of 0 is less than a y value of 1. So this would be false. Number 4, the graph has 2 maximums. A maximum is a point where the y value is the greatest. If we look right at this top right peak, we have a point at 21, 8.3. We have another point over here at about 9, 8. So while it might have 2 relative maximums, each of these points is greater than the points around them. 8.3 is a larger value than 8. So 21, 8.3 is the 1 maximum for this graph. So number 4 would be false. There is only 1 maximum. And number 5, about 21 seconds after he left his bike, he was the farthest away from it at about 8.3 feet. This is the point that we just pointed out was our maximum. So that would be the point where he is farthest away from his bike. So number 5 would be a true statement. Tyler filled up his bathtub, took a bath, and then drained the tub. The function B gives, remember that's our key word to look for, the very next thing will be the output, and that is the depth of the water in inches. Okay, so the depth is our output. T minutes after Tyler began to fill the bathtub. So the time after he began filling the bathtub is our input. They want us to explain the meaning of each statement in this situation. So we have B of 0 equals 0. So the first 0 is our input. That is the number of minutes after Tyler began to fill the bathtub. So 0 minutes, meaning he has not started the tub yet. The second 0 is our output, which is the depth of the water in inches. So this first one means that the bathtub starts empty. Next, we have B of 1, so that is the depth of the water 1 minute after Tyler began to fill the bathtub. Is less than the depth at 7 minutes, because this 7 is an input and the input is minutes after. Number 3, B of 9 equals 11. 9 is the input, so that's 9 minutes. 11 is the output, so that's 11 inches of water. So the depth after 9 minutes was 11 inches. Number 4, B of 10, so that's the depth after 10 minutes, equals B of 22, which is the depth after 22 minutes. And number 5, B of 20, which is the depth after 20 minutes, is greater than B of 40, which is the depth after 40 minutes. Function f gives the temperature in degrees Celsius T hours after midnight. So remember, the function gives the output using the input. So now they want us to use function notation to write an equation or expression for each statement. So we want the temperature, which is our function's output, at 12 p.m., which would be 12 hours after midnight. So this would be the function of 12. They don't tell us what the temperature is, so we can't write what it's equal to, but we can say that the function, when it's 12 hours after midnight, and that will represent that there is some temperature that it equals. Number 2, the temperature was the same at 9 a.m. and 4 p.m. Well, 9 a.m. would be 9 hours after midnight, so that would be F of 9. Same means equal to, and 4 p.m. is 16 hours after midnight, so that would be F of 16. Number 3. It was warmer at 9 a.m. than at 6 a.m. So 9 a.m. would be 9 hours after midnight, so we would represent that as F of 9. The word warmer would indicate greater than, and 6 a.m. would be 6 hours after midnight, so that would be F of 6. And finally, number 4, sometime after midnight, the temperature was 24 degrees Celsius. So we know the function name is f. We don't know how many hours after midnight, but they told us to use the variable t. So we'll say f of t, and this time they do tell us the actual temperature, so it equals 24 degrees. This graph shows the populations of Baltimore and Cleveland in the 20th century. B of t is the population of Baltimore in year t, and that would be the solid line. C of t is the population of Cleveland in year t, and Cleveland would be the dashed line. Number 1. Estimate B of 1930 and explain what it means in this situation. So 1930 would be the input, or the x value, and B is the solid line. So we want to go where x equals 1930, and we want to go straight up until we hit the solid line. Once we hit the solid line, we look to the left and we see what the y value is. And the y value is approximately 800,000. So this would mean the population in Baltimore was approximately 800,000 in 1930. Number 2. Here are pairs of statements about the two populations. In each pair, which statement is true? Be prepared to explain how you know. So, the first statement says B of 2000 is greater than C of 2000. So we go over until x equals 2000, and we go up. And we see that the solid line is greater, which is B, Baltimore. So that statement is true because in the year 2000, Baltimore had a higher population because they had a higher y value. B says B of 1900 equals C of 1900. 1900 is the x value, so we go up and we see that the blue line or the solid line for Baltimore is higher than the dashed line for Cleveland, so these are not equal to each other. The true statement is that B of 1900 is greater than C of 1900 because the solid line for Baltimore has a higher y value than the dashed line for Cleveland. And number 3, were the two cities' populations ever the same? If so, when. So populations would be the same anytime the two lines crossed each other. And we can see one point when X was 1910. So yes, 1910. And then if we continue to go, we see that the lines cross each other again around 1945. So those would be the 2 years where the populations were the same because the lines cross each other at those times. We start out with Baltimore having more people than Cleveland. Then they cross each other, and Cleveland has more people than Baltimore for a little while. And then they cross each other again, and Baltimore starts to have more people than Cleveland. Function A gives the area in square inches of a square with side length x inches. So function A gives the area in square inches. The area in square inches is our output. Using side length in inches as our input. Now we need to know that an area of a square is the side length times itself. So number 1 wants us to complete the table. We're going to take each of these x values and we're going to multiply them by themselves. So 0 times 0 is 0. 1 times 1 is 1. 2 times 2 is 4. 3 times 3 is 9. 4 times 4 is 16. 5 times 5 is 25. And 6 times 6 is 36. Now they want us to represent function A using an equation. So when we write function notation, we have the function name, capital A. We have our input in parentheses, which is x. And we have the rule that we followed, which was x squared. And that would be the equation. And number 3, sketch a graph of function A. We're going to look at the table, and every column in the table is a point pair. The top number is the x coordinate, and the bottom number is the y coordinate. So we're going to put our first point where x is 0 and y is 0 at the origin. Then we're going to put a point where x is 1 and y is 1. The next point, x is 2 and y is 4. The next point, x is 3 and y is 9. then x is 4, and y is 16. Then x is 5, and y is 25. And finally, x is 6, and y is 36. So these are our points. In context, we can have side lengths that are partial inches, and we can have areas that are partial squared inches. So we can connect our points and then draw our line that continues to go up as this square continues to get larger and larger. The graph shows the total distance in feet walked by a person as a function of time. So the graph shows the next thing is our output, the total distance in feet walked by a person. As a function of the next thing, time in seconds, is the input. Number 1, was the person walking faster between 20 and 40 seconds or between 80 and 100 seconds? So between 20 and 40 seconds, we increased from about 7.5 to 10. So we would say 10 minus 7.5 is our change in y. And we went from 20 seconds to 40 seconds. So 40 minus 20 is our change in x. That's 2.5 feet in 20 seconds. .5 divided by 20 is 0.125 feet per second. Now, between 80 and 100 seconds, we appear to have gone from maybe 13 feet up to 21 feet. So this could be 21 minus 13 for the change in y. And again, this was in 20 seconds. So 100 minus 80. We have a change of 8 feet in 20 seconds. Which is 0.4 feet per second. So we can clearly see that 0.4 is greater than 0.125. So between 80 and 100 seconds is when the person was walking faster. Number 2. Was the person walking faster between 0 and 40 seconds? So from 0 up to 10, we would say 10 minus 0, and that's from 0 seconds to 40 seconds. So 40 minus 0, that's 10 over 40, which is 0.25 feet per second. Or were they walking faster between 40 and 100? This appears to be 21 feet and 10 feet. And we said it was 100 seconds and 40 seconds. 21 minus 10 is 11. 100 minus 40 is 60. And 11 divided by 60 is 0.18 feet per second. We can see that 0.25 is greater than 0.18. So this person was walking faster between 0 and 40 seconds. These are the review questions for your test on Friday. Make sure you understand how to do everything on these problems. Remember to look over the study guide at what each question on the test will give you and what each question on the test will expect you to be able to do. If you have any questions, please use class time on Wednesday and Thursday to get clarification. Wednesday, we will do Khan Academy modules that will be over this same material, so you get more practice. Best of luck on your test. Study hard and do your best.